Hi everyone, my name is Tan. I'm from Johns Hopkins University. Today I'm presenting our work, namely on instant dependent values for offline reinforcement learning with linear function approximation. This is a joint work with Minjin, Sunil Gupta, Sveta Venkatesh, and Raman Arora. I will make contribution to the literature of offline reinforcement learning. In many domains, online interactions can be too costly to run and even lead to unsafe and unethical behaviors. Offline reinforcement learning is therefore preferred over online reinforcement learning because offline can be more feasible and enable a better generalization while utilizing large datasets and diverse prior experiences. So our work is also related to function approximation in reinforcement learning. In practical setting, we will never get enough data to learn each state individually. So scaling the sample complexity linearly with the space size is thus undesirable. We need to we need function approximation to generalize from collected state to unvisited states. In this work, we consider episodic time inhomogeneous Markov decision process. So here, S is the state space, A is the action space, capital H is the episode length, P is the transition kernels that map a state's action pair to a probability over the next state, and R is the reward functions that map a state action pair to a real value. As its step H, the agent takes an action AH. So in response, the environment yields a reward RH and transitions to a new state uh, SH plus 1. So the interaction proceeds iteratively until the end of the episode. Upon completing one episode, the agent environment interaction is started all over again for a new episode. A policy in Markov decision process is a mapping from a state space to a probability over the action space. The essential quantity in Markov decision process is the action value function, which is the expected value of the total reward accumulated by the agent starting from certain time step and certain states in action. So an optimal policy is a policy that maximizes the value function. Another central element in Markov decision process is Bellman operator. The Bellman operator quantifies the, the value one would expect to obtain at certain time step h, given that we know the value at step h plus 1. So essential result in Markov decision process says that the optimal action value function Q star is a fixed point of the Bellman operator. So in other words, evaluating the Bellman error gives some goodness justification of how close a value function is close to the optimal one. This is also the main intuition for value-based learning in reinforcement learning, and also a generate roadmap that we take in this work. In the offline setting, we are given a fixed dataset of previous interaction experiences. So the offline dataset consists of K episodes collected by some unknown behavior policy for mu. It's important to note that in offline reinforcement learning, no further interaction with the MDP is allowed. So fixed offline dataset is all information we have for learning. The goal of offline reinforcement learning is to learn from the fixed offline dataset a policy pi hat such that its value suboptimality is as small as possible. The value suboptimality measures how close the value of a policy to that of an optimal policy. That being said, uh, the smaller the value suboptimality, the better. So the learning protocol for offline reinforcement learning is that an offline reinforcement learning algorithm has access to only the fixed data set and possibly some function class to estimate the value function. The key research question in our work is how to design provably instant and efficient offline reinforcement learning algorithm in function approximation setting with the widest data collection assumption possible. So by instant efficient, we mean that The algorithm should be able to leverage any instant specific information to accelerate the learning. So efficiency can mean two things. Sample efficiency means the required number of samples is independent of the state space height and polynomial in other factor. Runtime efficiency means the algorithm runs in polynomial time. My data collection assumption means that the offline data does not need to cover the entire state action space, and it can be collected adaptively by running some adaptive algorithm. Existing results obtain finite value suboptimality and nearly match the lower bounds. However, these results are inefficient where the state space size is large, and they bound scaled polynomially with the state space size. The solution is to consider linear MDP. So linear MDP is a class of MDPs that admit nice linear representations. Specifically, the reward function and transition kernels can be represented in terms of the linear function of some non-feature phi. Linear MDP model is simple enough to have closed form solution to least square value iterations, yet complex enough to contain many fundamental challenges in function approximations. A well-known result for offline reinforcement learning in linear MDP is the algorithm pessimistic value iteration algorithm of James 2021. So the key algorithm idea is that it explicitly construct a lower confidence bound of the value function from the offline data. As a result, a finite value suboptimality in K is obtained under various assumptions of the data coverage. The advantage of this result is that the bound is independent of the state space size S. Another advantage of the bounds is that the bounds are of the minimax type. It means that they bounds hold for all instances, even in the worst case. However, the limitation is that assuming a worst case setting is too conservative, because in many natural settings in nicer instances, the rates can be faster than 1 over square root of k. So in this work, we argue that to circumvent the minimax lower bounds and explain the fast rates in practical setting, we should consider intrinsic instant-dependent structure of the underlying MDP. So here we review existing instant-dependent bounds for offline reinforcement learning. The first such work is Hill 2021 that studies instant-dependent bounds under the assumption with exponentially high probability the gap at every state reachable by any policy cannot be too small. So additionally, in the uniform feature coverage assumption, they show that fit to Q iteration, a simple algorithm, has value suboptimality rate of 1 over k in linear MDP. So the advantages of the results is that the result hold for various function classes and use a weak version of gap assumption. The main limitation is, however, there are some uniform feature coverage and independently collected data. So these assumptions are among the strongest assumptions about the offline data that significantly limit the application scope of the result for practical setting. The second instant-dependent bound work also relies on the gap assumption. So a recent work one, published last year, used gap information to show fast rates of value suboptimality. The data coverage assumption they use is single policy concentrability, which is much milder than the uniform data coverage assumption. However, the value suboptimality rates scale with the state space size S, which is undesirable for practical setting where the state space is exponentially large. They also require the episodes were collected independently, which is also a strong assumption. In practice, offline data can be adaptively collected by running some adaptive learning algorithms. This adaptively collected data violates the key assumptions in the existing works of instant-dependent bias for offline reinforcement learning. So in D1 2020, scale with the state space size and require that the data are independently collected, while Wu paper require uniform data coverage assumption. In our work, we address all these shortcomings in this paper with linear MDPs. So our algorithm built up on pessimistic value iteration algorithm of June 2020 21st. Specifically, we explicitly construct an uncertainty quantifier V and subtract it from the empirical value estimate to obtain a lower confidence value. Additionally and importantly, we add two modifications, bootstrapping and constraint quality extraction. So bootstrapping means we split the offline data into k subsets that mimics the data obtained by an online learner. We then apply offline reinforcement learning algorithm in each of the data subsets to form an ensemble of value estimates. By constraint policy extraction, given its value estimate, we extract the policy that is most greedy with respect to the value estimate among all policies that are supported by the behavior policy view. So the key intuition of the design is that it can effectively deal with adaptively collected data while leveraging the gap information as states supported by the behavior policy. The first instant-dependent bias of our result is gap-dependent bias, where we show a fast rate of value suboptimality of offline reinforcement learning with linear function approximation. The key advantage in our result is that the bias is independent of the space size S, making it suitable to function approximation. Notably, our fast rate result holds under the my assumption of single policy concentrability and adaptively collected data. To the best of our knowledge, our result is the first of its kind for fast rates under such my data coverage assumption in linear MVP, and our lower bound shows that the upper bound is tight in terms of the number of efforts of k and the minimal gap delta mean. On the technical side, we count the number of times the gap as states supported by the behavior policy and see a certain threshold, and we also use the peeling technique to obtain fast rates. For our second instant-dependent bias, we show that when the linear feature in the linear MPP is good, in the center the linear feature at the states supported by the behavior policy span those by the optimal policy, our algorithm obtains absolute zero value suboptimality when the number of samples exceeds certain instant-dependent threshold. We also extend our gap-dependent bias to the linear mixture model and obtain the fast rate in this case under the gap assumption and my assumption data coverage. So in summary, we have designed a provably efficient algorithm for linear function approximation with polynomial sample and runtimes. So our algorithm is a combination of least square value iteration, lower confidence bound, bootstrapping, and constraint policy extraction. As a result, we obtain instant dependent bias under gap assumption and good linear feature. Thank you for your listening. For more details, please check out our poster at the conference or our archive version.